Hello everybody. Now we will be going over the portfolio optimization problem with two assets, and I generically called these two assets as bonds and stocks. And what we will do next is we are given, let me just go ahead and highlight it. We are given that the annual return for bonds is 12%, and it has a standard deviation of 5%. And the annual return for stocks is 20%, and it comes with a standard deviation of 10%. So comparing those two assets, it seems bond securities are more desirable in terms of the lower level of its riskiness, but at the same time, stocks are more desirable in terms of the higher level of its return. So as a result, it looks quite plausible that diversification will have some benefits for potential investors. Lastly, we are told that the correlation coefficient between the bond and stock securities is 0.25. Just to remind you, a correlation coefficient is always a number between -1 and 1. As it gets closer to +1, it means the securities are more perfectly correlated when they are exactly equal to 1. And when it gets closer and closer to -1, it means they are perfectly negatively correlated. Anything which is between -1 and +1, it shows some sort of correlation between bonds and stocks, but not perfectly correlation. Either positive or negative, not perfectly correlated. In the case of even when it is 0, it means there's some sort of correlation. Well, I should revise it. There is, even though there's no correlation, it will have a bearing on the way we solve the problem. All right, so now given those two assets with their respective features, now our goal is to construct a portfolio that is finding weights, WB and WS, weights WB, and so the proportion of your portfolio that you want to invest in bonds and or stocks, right? They should add up to 100%, obviously, right? So for instance, we can decide to invest 50% in stocks and 50% in bonds. That would be one possible scenario. However, we have a certain objective, and our objective is to maximize the expected return of the portfolio, which is given by this relationship. Let me just go ahead and so this is the objective function that we are maximizing, the expected portfolio return on the portfolio, which is basically weighted average returns. So 12% return for bonds, and this is the proportion of our portfolio invested in bonds, and 20% return on stocks, and this is the proportion of the portfolio invested in stocks. So that expression is the one that we want to maximize, and like we said earlier, we want to make sure that we spend all of our money for bonds and stocks. And secondly, we're given this additional condition that the portfolio variance, that's what that product of those three matrices are, the variance of the portfolio, the expected variance of the portfolio, we want it to be less than or equal to 0.005. So this number is just given to us. And by the way, this is just equal to 1/200 if you want to work with fractions. And indeed, we can convert each of these numbers into fractions as well. So given these two constraints, what are the weights? So what is the proportion of the portfolio that should be invested in bonds and stocks that will maximize our objective function, namely the expected return of the portfolio? All right, so let's just go ahead and solve the problem. The best way would be to first, arguably the best way will be by first working with that constraint, expanding out that constraint that we have here, especially the second constraint regarding the expected variance of the portfolio. Once we expand it out, we want to substitute an expression, for instance, express WB in terms of WS, I would say, right? So the weight of the bond is 100% minus the weight of the stock. 100% is just equal to 1, right? So we can we can just do that simple substitution. But first, let's go ahead and start with that expression at the bottom. Let's make sure we know how to expand that out. And let me just remind you that this is a 1 by 2 matrix. The one in the middle is a 2 by 2 matrix, and the one at the end is a 2 by 1 matrix. Because we have a product of 3 matrices, we can go ahead and multiply the last 2 matrices first. Can we do that? Yes, we can, simply because the number of columns of the first matrix is equal to the number of rows of the second matrix. Once we multiply these two, the outcome will be 2 by 1 matrix. So let me just go ahead and write that down. So the outcome will be a 2 by 1 matrix. And then because the very first one was a 1 by 2 matrix, again, the number of columns of the first matrix is equal to the number of rows of the second matrix. As a result, the final outcome, when I further multiply these two, will end up being a 1 by 1 matrix. But a 1 by 1 matrix is just a number. So on the left hand side, we will end up with a number which we want it to be less than or equal to 1 over 200. Does that make sense? So that's the condition. So let's just go ahead and multiply the last 2 matrices, that 2 by 2 matrix with that 2 by 1 matrix first, and then I will go ahead and further multiply it with that 1 by 2 matrix. We're going to first solve this manually, and then like I usually do, we will solve that very same problem using Microsoft Excel as well. All right, so let me just go ahead and start on the side. So I will, like I said, let me first go ahead and keep that very first matrix, WS, that's a 1 by 2 matrix. But now multiplying that 2 by 2 with that 2 by 1 matrix, we know that the outcome will be a 2 by 1 matrix again. And in fact, I can do one more thing before I proceed further. I can just substitute these values into the expression. That matrix, that 2 by 2 matrix, is a variance covariance matrix, and it's very easy to derive these numbers. We already know sigma b, the standard deviation of the bond, is 5%, or 1 over 20. So squaring it, we will get 1 over 400. So let's just write that down, 1 over 400. And the other diagonal entry, sigma s squared. Sigma s is the standard deviation of the stocks, 10%, which is 1 over 10, squared. That will give us 1 over 100, 1 over 100. Now, the only thing remaining are the off-diagonal entries, which turns out to be the same thing. The covariance of bonds and stocks versus the covariance of stock and bond, they are the same thing. So how do we calculate the covariance? It's just the product of the individual standard deviations and the correlation coefficient. So in our case, it's 5% times 10% times 0.25. 5% is just 5 over 100, or if you want, we can simplify it as 1 over 20. 10% is over 1 over 10, so 1 over 20 times 1 over 10 is 1 over 200, and 0.25 is 1 over 4, so 1 over 200 times 1 over 4 is, actually, let me just write down all of this down below, because so that we can have a record of this. So the covariance of the bond and the stock is equal to the standard deviation of the bond times the standard deviation of the stock times the correlation coefficient of the bond and the stock. So the standard deviation of the bond was 1 over 20, 0.05. The standard deviation of the stock was 1 over 0.1, which is 1 over 10. And the correlation coefficient between them was 0.25, which is 1/4 basically. I prefer to work with fractions somehow, but some people, they just prefer decimal representation, which is perfectly fine as well. So 1 over 20 times 1 over 10 is 1 over 200, times 1 over 4 is 1 over 800. So that's the covariance between the bond and the stock security. So 1 over 800 we said. So we can just go ahead and substitute that into our expression as well, 1 over 800 here too. And we still have the second, the transpose of the same vector as a, so there you go. And we want that to be less than or equal to 1 over 200. One thing which we can do immediately is to multiply, say for instance, both sides of this expression by, why not, 800. If we multiply both sides of this expression by 800, of the three matrices on the left hand side, I just need to multiply one of them, all entries of one of them, by 800. So I can just go ahead and multiply the middle one so that we can get rid of all those fractions, if that makes sense. So that would imply, as a result, we would get WB, WS, and the one in the middle ends up being 2118. And the last, oops, how did I manage to do that again? And we have WB, WS less than, or because I multiplied both sides by 800, on the right hand side we are left with 4. Now we can go ahead and multiply things out. I will go ahead and multiply the second matrix with the third matrix. We still have the first matrix intact. And a 2 by 2 times a 2 by 1 matrix will end up being a 2 by 1 matrix. So 2 times WB, 2WB plus WS, and then WB plus 8WS. That's it. That's still less than or equal to 4. Now let's go ahead and multiply that 1 by 2 with that 2 by 1. The entry will be end up a 1 by 1, just a number, so I can remove that matrix notation. So we have WB times 2WB plus WS. Let's just do it in 2 steps, I guess. WB times 2WB plus WS plus WS times WB plus 8WS, and that whole thing, let me move these things to the side actually, that whole thing is supposed to be less than or equal to 4. Let me just get rid of that arrow over there, and that implies, okay, so when you bundle the like terms together, we have 2WB squared, we have WBWS here, WBWS, so 2WBWS, WB times WS, and then we have 8WS squared, 8WS squared less than or equal to 4. We can go ahead and divide both sides by 2 and then move that 4 to the left hand side. So, and it ends up being WB squared plus WBWS plus 4WS squared minus 4 is less, minus 2. We decided to divide by 2. Minus 2 is less than or equal to 0. And now that we have that condition, so we were able to significantly reduce that. So this is the condition that should replace the original condition with the matrix form. So we no longer want to use the matrix form. This new expression is way simpler than the original one. So what I'm going to do, I'm going to rephrase the original problem one more time, and let me just do it over here in that space. Oops, did I press the, okay, there you go. So let me just go ahead and do it, the new representation of the problem right in that square. So basically, let me just use a different color here. The problem that we want to solve is the following. We want to maximize, okay, or maybe let me do it this way. Choose WB and WS such that the objective will be satisfied. Namely, the objective is to maximize the portfolio return, which is just 0.12 times WB plus 0.2 times WS, right? So let's write that down. 0.12 is basically 12 over 100, and I can simplify both 12 and 100 by 4, so it ends up being 3 over 25 if you want. So that's just 3 over 25 WB plus 0.20 is just if you want 1 over 5, right? So all right, if you want, I can write it as 5 over 25. It's the same thing. Okay, let's just write 1 over 5 WS. So I want to choose WB and WS, namely construct a portfolio, decide on what should be the weight of weight of bonds and weight of stocks in my portfolio, what proportion should be invested in bonds and what proportion should be invested in stocks, such that this objective function is maximized. So this is just the expected return, right? Given the following conditions are satisfied, namely that I want to make sure these are the only two assets that I'm investing in. WB plus WS is equal to 1. And secondly, now we have the second condition. We want the somehow a condition relating to the variance. We want WB squared. Let me and WB squared plus, let me write that down carefully, WB WS times 4 times ws square minus 2 is less than or equal to 0. That's it. That's the problem. So let me just move everything to the side now. That's the problem that we want to solve. I think we already talked about a very good strategy. The very good strategy would be to just express WB in terms of WS. For instance, we will use a substitution technique. Substitution. So if I use a substitution technique, I can just go ahead and replace WB with 1 minus WS from the first expression. So therefore the problem then reduces to the following. So therefore the new problem that we want to solve is the following. So this way I'm able to just get rid of this condition. So ultimately the problem will reduce to the following: 3 over 25. WB now will be replaced with 1 minus WS plus 1 over 5, and WS is just WS. And I can do one more step here if you want. 3 over 25 times 1 is 3 over 25, and minus 3 over 25 WS plus 1 over 5 WS. 1 over 5 WS is just 5 over 25 WS. Minus 3 over 25 is just 2 over 25. 2 over 25 WS subject to, and now we have the new condition. So for that new condition, let me first do the bashing, and then let me just put that condition right here, right? So let's just do it over here. So WB will be replaced with 1 minus WS square plus WB is again 1 minus WS times WS plus 4 times WS square minus 2 is less than or equal to 0. But then this implies, okay, expanding things, 1 minus 2WS plus WS square plus WS minus WS square plus 4WS square minus 2 is less than or equal to 0, which implies, okay, let's combine the like terms. The WS squares here cancel. So we have 4WS square minus 2WS plus WS, so minus WS plus 1 minus 2, so that's just a minus 1 is less than or equal to 0. So that's the condition we want to put here. 4WS square minus WS minus 1 is less than or equal to 0. That's it. That's the new problem. Do you guys see how we started with a certain objective function, an objective which we kept revising and refining over and over? And well, why are we doing that? So that we simplify the problem, right? So the new problem is basically this: maximize this, make it as high as possible as long as you satisfy this condition. You might say, hey, if the objective is to maximize this thing, why don't we just pick WS to be equal to 1? That's the maximum WS can be, right? Assuming WB and WS are both greater than or equal to 0. Maybe I should have mentioned that earlier. So that condition, yeah, I should have mentioned this way earlier. I'm just constructing portfolios with no short sell. So find weights WS, WB and WS which are greater than or equal to 0. So that condition is important. So we want the revised problem is now is this: WB and WS greater than or equal to 0 such that. And now the latest newest version is this, right? Where again, let me add that, where, let's write that down. Again, we are finding WB and WS where WB and WS are both greater than or equal to 0. So given the fact that WB and WS, both of them are greater than or equal to 0, but they sum up to 1, so therefore each individual WB or WS cannot be more than 1. So one idea is, why don't we just substitute a 1 here? So that will maximize this function. However, if you were to substitute a 1 here, the 1 wouldn't have satisfied the condition here. If you plug in 1 here, 4 times 1 square, this one is a WS, obviously. WS, 1 square is just 1, 4 times 1 is 4, 4 minus 1, that's a 2, 2 is greater than or equal to 0. That doesn't even satisfy the desired condition. So therefore, okay, so let's just move everything out. So what is the WS, what is how high WS could be such that this condition is still satisfied? WB and WS, we want both of them to be greater than or equal to 0, but at the same time we want to satisfy this condition as well. So what I will do next is the following. Well, obviously I'm solving the problem manually. It's very unlikely you guys will end up solving the problem manually. So I think companies, professional companies, what they do is once in a year they revise their models. But once there's a model, the model is being used like for periodically, like for a long period of time, maybe for 6 months, a year, and then a year later the analysts inside the company, they prefer to revise the model. But until it is revised by financial analysts or business analysts, the model is being used on a daily basis by people in the company. So it's really, financial modeling is in terms of the hierarchy, is the higher end of the whole thing, and it is the part which is both exciting but at the same time challenging as well. Once a model is developed, you can easily code it on Excel, and then Excel will do it most of the time. That's why usually it's important to know what's going on behind the scene. So like it's usually preferred that you understand how the program works, because if you just blindly memorize the program, it will be very easy to use the program. It will probably just take you 1 or 2 hours of training, right? Or maybe 5-6 hours of training, or at most a week of training. For a week you will struggle, but a week later you will know how the program works. But that doesn't mean you know the process itself. If you don't know the process, what's going to happen is that skill that you developed 6 months later, a year later, if you move to a new company or a new location, or for some reason your company decided to revise the model, suddenly you realize that your skills are obsolete, right? So that's why understanding the process behind, the math behind things are very important. Anyhow, so because that's our objective, but at the same time we want to make sure we satisfy this constraint, what we will end up doing is the following. So first, let's try to understand this constraint, which I can easily use the quadratic formula to understand, I guess. Using the quadratic formula, so let's write that down. Quadratic formula, I don't know if you guys remember this, but hopefully you do. Formula. I'm going to apply the quadratic formula for this expression so that we better understand what's going on. And it turns out that when I apply the quadratic formula, that gives me the roots. And obviously I'm only interested in the positive roots. So the roots will end up being minus 1, which is 1, plus, let me write down both roots and then we decide which of the two roots we want to use. B squared, which is 1 minus 4 times minus 1, all divided by 2 times 4. And that thing comes out as 1 plus or minus square root of 1 plus 16, which is 17, all divided by 8. WS. That's it. So now what does that mean? What it means is the following. So if you were to graph it, so we have WS, and here is the graph of this function. So obviously square root of 17 is roughly 4.1 or 4.2. Adding 1 to it, you will get 5.2. Dividing it by 8 will be like something a little bit more than 0.5, right? So actually I have a calculator in front of me. Let me do an exact calculation. 17 square root plus 1 equals divided by 8. So 0.64 roughly. So 0.64 here, 0.64, versus if I were to pick the negative one, so 17 square root plus minus plus 1 equals divided by 8, 0.39, but minus. So maybe closer to 0, so minus 0.39. So what it means is the following. This is the constraint that we have in this problem is a parabola. And as a result, the shape will be the following. As you guys can imagine, a quadratic will have a parabola shape like this. Now, our goal is to maximize WS as much as possible, as long as this expression is less than or equal to 0. So meaning as long as this parabola expression for WS square minus WS minus 1 is less than or equal to, meaning that as long as that thing is below the x-axis, so we want that thing to remain below the x-axis, which is basically this range over here. And within that range, the highest value that we can take is exactly this endpoint. So this endpoint, which was, like we said, 1 plus square root of 17 all divided by 8. That's WS. And so that's our claim. We claim that the answer to this problem is, let me give exact answer, 17 square root of 17 plus 1 equals divided by 8, 64.0388%. So this is just equal to, and that's just equal to 0.0388, or let me just write it as a percentage, 64.0388%. That's it. So we were able to find WS. WB is easy. WB, the proportion of the budget, investment budget that should be allocated, or the portfolio that should be allocated to the bond securities should be 100% minus that number, WS, let's write it. So if I were to subtract it from 100%, that ends up being, actually, let me just do it here, 35.9612. 35.9612%. So that's the proportion of the portfolio that should be invested in bonds. And given these proportions, what is the, yes, there you go. What is the solution? So what is the expected return? Maximize the expected return. Let's write that down and finish this problem. Maximum expected return of portfolio, given that constraint, given that we don't want the risk to be more than 1 over, given that we don't want the variance to be more than 1 over 200, is the following. Let me just bring this back here. All right, perfect. Is equal to, well, 3 over 25, or let's just write it as a fraction. I think this is 0.12 as a fraction, plus 2 over 25 times WS. WS is this number. So let me do the calculation. 2 over 25 equals 0.08 times, actually, let me write it down. 0.08 times WS, which is 0.640388. And that is simply equal to, so let me just go ahead and do the final touch-ups. 640388 equals plus 0.12 equals 17.1230, or let's just write it like that, 17.12%. That's it. We were able to construct a portfolio, and our portfolio consists of 64% stocks and roughly 36% bonds. And with that portfolio mixture of securities, we can achieve a 17.12% return without exceeding a variance above 0.005 or 1 over 200. That's the solution to this constraint optimization problem, namely this portfolio optimization problem. And next I will be solving that very same problem using Excel, and I assume most of you guys will be using Excel when you are solving the actual problem assignment as well. Hope to see you guys in our next lecture.